This section is all about the hyperbolic functions. Now, this is not a section that will appear on a test or on the final exam, but you do have a homework assignment based on this section. So that's what this video is meant to help you accomplish. So hyperbolic functions, they arise from comparing the area of a semicircular region to the area of a hyperbola. So a circle, a semicircle looks like this. Y equals the square root of 1 minus x squared would be one example. The circle would be x squared plus y squared equals 1. And this hyperbola here, or half of the hyperbola, would be y equals the square root of 1 minus x, or 1 plus x squared, where the hyperbola was negative x squared plus y squared equals 1. So you can see that these are two very similar functions. The only difference is actually the negative sign here and here, and then the positive and the negative here. So when you compare these two areas, you wind up with these definitions here. So notice this little h here. This little h indicates that you're actually looking at the hyperbolic sign instead of the regular sign. And the definition here is that this is e to the x minus e to the negative x divided by 2. This one is e to the x plus e to the negative x divided by 2. And this one is the hyperbolic sine divided by the hyperbolic cosine. So really, these are new, okay? And the reason why we actually name, or one of the reasons why we actually name them the hyperbolic sine and we kind of relate them back to those trigonometric functions is because they do hold a lot of the same relationships, sine and cosine, and then these other definitions hold a lot of the same relationships as the real sine and cosine that we're used to. They have a lot of similarities with trig functions, but they're not exactly the same. So if you wanted to look at the graphs, you can see that there are some similarities, but it's not exactly the graph of sine of x. And in some ways, they even look almost like inverses, but they're not quite exactly. You don't want to read too much into that. Now, some of the applications of these things, they actually show up in a lot of applications. So pay attention to this graph right here, the hyperbolic cosine, and then this is an example of what's called a catenary. So you can actually model like a wire that's strung between two points that are at the same height and then kind of dips with gravity. This is actually a hyperbolic cosine if you wanted to model that wire. Just like with trig functions, there's a whole bunch of identities that are held by hyperbolic functions. You want to be careful with these because they're not exactly the ones that you learned with trig functions. So notice the hyperbolic cosine squared minus the hyperbolic sine squared is equal to 1. Normally you would have a plus there if these were just regular sine and cosine, but here you have a minus. So do be careful with these properties and these identities. They're not exactly the same. They are pretty easy to prove, though, as long as you understand the definitions and you know how to use exponentials. So if I want to prove the fact that the hyperbolic cosine squared minus the hyperbolic sine squared is equal to 1, I'm going to start off with the definitions of each of those. So this would be e to the x plus e to the negative x divided by 2 squared. And this one would be e to the x minus e to the negative x divided by 2 squared, and I want to show that that's 1. So if I do a little work on this, I'm going to FOIL out the top. That would be e to the 2x plus e to the x, e to the negative x, plus e to the negative 2x. If I square that, remember I'm just multiplying the power, divided by 4. This one is going to be e to the 2x minus e to the x, e to the negative x. And actually I need a 2 here and here, plus e to the negative 2x divided by 4. So this will be e to the 2x. This actually becomes a 1 because you add them together and get e to the 0. So 2 times 1 plus e to the negative 2x divided by 4. And I do have a common denominator, so let's just go ahead and distribute these negatives. We'll have minus e to the 2x minus negative 2 times 1 minus e to the negative 2x. And from here you can see that some things start to cancel. We've got e to the 2x and negative e to the 2x. We've got e to the negative 2x and negative e to the negative 2x. So this ends up being 2 plus 2 over 4 which is 1. So you can see that that is a true statement. Some of the derivatives and integrals of hyperbolic functions. These are going to have very similar relationships to the derivatives of the regular trigonometric functions as well. So one of those that I want to prove that the derivative of the hyperbolic cosine is equal to the hyperbolic sine of u times u prime. So we're just going to use the definition again of the hyperbolic cosine. So this is the derivative with respect to x of e to the u plus e to the negative u divided by 2. So I'm going to bring the 1/2 out and then split up the derivative. So I've just brought the 1/2 out and then I've split this up into two derivatives, the derivative of e to the u and the derivative of e to the negative u. So the derivative of e to the u is going to be e to the u times u prime. And the derivative of e to the negative u is going to be e to the negative u times negative u prime. And this is all times 1/2. So let me put my 1/2 in parentheses here. So doing a little bit of algebra here, you can see that you do have a u prime on both of these. So I'm going to kind of factor that out. And that would leave me with e to the u minus e to the negative u, and then I'm going to divide that by 2. And this portion right here is the hyperbolic sine of u. So we do get the hyperbolic sine of u times u prime. So that would be where that comes from. And just to work some examples that use this, if I wanted to find the derivative of f of x equals the natural log of the hyperbolic sine, so we're trying to find f prime of x, which is the derivative with respect to x of the natural log of the hyperbolic sine of x. So if I let that be the natural log of u, I know that the derivative is going to be u prime over u. I just need to know what u prime actually is. So u is the hyperbolic sine of x, and u prime is going to be the hyperbolic cosine of x. So this gives me the hyperbolic cosine divided by the hyperbolic sine. And we do know that that follows the rule that this is equal to the hyperbolic cotangent of x. So that would be my answer there. For this one, I would be looking for the derivative with respect to x of the hyperbolic secant of 3x squared. So this is really just the derivative with respect to x of a u squared, which we know is 2u to the first power times u prime. So if u is the hyperbolic secant of 3x, then u prime is going to be, remember, the derivative of the hyperbolic secant is negative hyperbolic secant, hyperbolic tangent, but then we need to multiply by that kind of internal u, u prime, so that would end up being a 3. So here we're going to have 2 times the hyperbolic secant of 3x, and then that's going to be multiplied by negative 3 times the hyperbolic secant of 3x times the hyperbolic tangent of 3x. So this ends up being negative 6 times the hyperbolic secant of 3x squared times the hyperbolic tangent of 3x. And that is my answer. When you're entering these answers in WebAssign, be very careful, because if you don't use the hyperbolic version of this, you will get it incorrect. Any of the applications that we've done involving these types of functions, or involving derivatives and integrals, we can do with these types of functions as well. So if I want to find the relative extrema of x minus 1 hyperbolic cosine of x minus the hyperbolic sine of x, f prime of x, for this one I would have to use the product rule, so f would be x minus 1, which means f is 1. G would be the hyperbolic cosine of x, which means g prime would be sine of x, hyperbolic sine. And if you need to check back to your formula, you know that that is actually not the negative hyperbolic sign for these. It doesn't turn negative. So f prime of x is the derivative with respect to x of this product fg minus the derivative with respect to x of the hyperbolic sign of x, because we do have the two separate pieces going on here. So this is going to be fg prime plus gf prime, and then this part on the end is just going to be the hyperbolic cosine. So when I go to plug this in, I get x minus 1 times the hyperbolic sine of x plus the hyperbolic cosine of x times 1 minus the hyperbolic cosine of x, and you can see that these do cancel out. So I end up with just x minus 1 times the hyperbolic sine of x. Now remember, I'm trying to find the relative extrema, so I would set each of these equal to 0 to find the critical numbers. So this one gives me x equals 1. This is actually e to the x minus e to the negative x over 2 equal to 0, and the only place where this is going to be equal to 0 is if e to the x equals e to the negative x. So if I were to take the natural log of both sides, that tells me that x has to be equal to negative x, which means x equals 0. So I might be able to do the second derivative test here. So this was, remember, f prime of x. F double prime of x, I would use f equals x minus 1, so f prime was 1, and I would use g equals the hyperbolic sine of x. So g prime would be the hyperbolic cosine of x. So this is going to be f g prime plus g f prime, which is x minus 1 times the hyperbolic cosine of x plus 1 times the hyperbolic sine of x. So my critical numbers, if I wanted to use the second derivative test, my critical numbers we found over here were 0 and 1, and if I plug those into f double prime, if I plug a negative 1 in here, this is going to be 0. The sign here is actually going to give me a negative 1, which is less than 0, because I would end up with, just plugging this in, that's what I would end up with. And then if I were looking at the, this one right here, I would have negative e to the first power plus e to the negative first power divided by 2. And you can evaluate this on your calculator and just see this gives you a number that is also less than 0. So this means that this is a relative max, and this is a relative max as well. So since f of x was equal to x minus 1 times the hyperbolic cosine of x minus the hyperbolic sine of x, f of 0 is going to be negative 1 times the hyperbolic cosine of 0 minus the hyperbolic sine of 0. So that'll be negative e to the 0 plus e to the 0 over 2 minus e to the 0 minus e to the 0 over 2. So that ends up being, let's see, that's negative 1 minus 0, or negative 1. And then f of 1 will be 0 times the hyperbolic cosine of 1 minus the hyperbolic cosine of 1. So this goes away, and I just have negative e to the 1 minus e to the negative 1 over 2. And that ends up being, let's see, we'll just write it as negative e plus e to the negative 1 over 2. You don't have to simplify it any more than that. So these are my relative extrema. Taking a look at a couple of integrals, if I let my u here be 2x, u prime would be 2. So I can multiply by a 2 on the inside and a 1/2 on the outside, which gives me 1/2 times the integral of the hyperbolic cosine of u with respect to u, because we actually have the 2 dx here that we need. So this would be 1/2 times the hyperbolic sine of u plus c, or 1/2 times the hyperbolic sine of 2x plus c when I plug that back in. And then for this integral, we would have our u is the hyperbolic sine of x, so u prime would be the hyperbolic cosine of x, which means that this is the integral of u squared du, which is u cubed over 3 plus c, which is the hyperbolic sine of x cubed over 3 plus c. You should also be aware that there are inverse hyperbolic functions. We're not going to go into detail on how to use these or how to deal with these, but you can think about it this way. If the hyperbolic sine is based on e to the x, the inverse of the hyperbolic sine would have to be based on natural log. So that's where these definitions come from. They just literally are finding the inverse of those e to the x definitions. And you can see what their graphs would look like. Again, don't get too bogged down in this. I mostly just want you to be aware that they exist. And then you can actually see the relationship more between these and the regular inverse trigonometric functions, because they are similar, but they're not exactly the same. But they take on these same kind of patterns when you're finding the derivatives and the integrals. So just be aware that these exist. You do not have to learn all of these formulas. They do exist in a lot of applications. So that's really what you want to take away from this.